Hi. This is something very preliminary and exploratory. We're trying to, that's related to our overall effort to study the sun in low-frequency radio waves. These are some collaborators. So this is kind of what the sun looks like in low frequencies between 79 and 25 megahertz, imaged with the LOFAR telescope, which is a massive pan-European radio telescope that operates between approximately 20, let's say, megahertz and 250 megahertz. So you can see obviously the resolution plays a role. This is quiet time imaging of the sun, snapshot images. So what we did in this work was try to sort of improve the resolution, the way that the sun looked, with an initial goal to do something like lucky imaging, so basically to filter out the bad images. The resolution on the data that we worked with is a quarter of a second per sample, and the observation itself is 4 hours long. So this graph shows on the 4 panels the 4 different correlations. So these are the amplitudes of the visibilities over the entire observation, and basically these are the 253 baselines between different LOFAR stations that we used. So the data in the low frequency, or the LBA, low band antenna part of the LOFAR telescope, are calibrated instantaneously, basically, because they're parallel observations of the target, which in our case is the sun, and a calibrator source. So at every sampling time step, there is a calibration solution. So these data were first reduced, calibrated, using calibrator source on the sky and the standard LOFAR software for doing this. And the result is a so-called measurement set, which is a product that contains all these visibilities. And then via a magical process called the clean algorithm and the so-called WS clean code, we arrive at images of the sun, actually. So what we wanted to do was do something to remove abnormal visibilities, amplitudes, and phases, so that we could get better images. Okay, so you can see here for a single baseline, that is 2 stations, the correlations between the signals received at 2 LOFAR stations, the amplitude and phase after the correction, the calibration over the entire observation. There were some issues at the end over here, so for the rest of the work we've removed all these time steps towards the end of the observation, and the different colors here represent the different correlations for the antennas, because they're cross dipoles, so you correlate the signals. So we take the extremely high visibility amplitudes as a sign of corrupted observations, and try to, due to incorrect calibration solutions, anospheric interference. So whether this criterion is correct or not is a separate question. But what we did was perform k-means clustering on the amplitudes and phases. I'll show in a second the rest of it. And we did that at each sample. So we have 253 points repeating. So we did k-means at every time step, so 50,000 of these time steps. First, what we did was evaluate the k parameter using these different methods. And so we arrived at a sort of an eyeballs evaluation number of 5. And so we used that for the rest of the work. And so we have 5 different experiments. So first we only apply k-means to XX visibility amplitudes, XX visibility amplitude and phase, and then all the amplitudes separately, all the phases separately, and then XX phase, XX amplitude and phase, and then YY amplitude and phase. And this is a cutoff. So basically what we did was when we applied the k-means, we say remove, so there's a cutoff at remove the highest 2 clusters. So the points with the highest values, the last 2 clusters were removed. And so we arrive at this cutoff, which is the lime color, I guess, here, over the entire observation. And then we generate images at every hour. So we average over 1 hour of observation. So here I'm just showing examples of the first hour of observation. This is the original image, and then we see a significant improvement to the resolution, so to speak, because the goal was to eventually apply automated detection of features in the low frequencies, which, to my knowledge, has not been done, or at least successfully. And so you can see these are the different results. I found, and this is preliminary again, that there wasn't such a big difference on the display. Probably you'll see some variations, but so far this is where we're at, and we've had some conversation, but I welcome any suggestions for improving this. And as I said, we've done it on a single dimension as well as multiple dimensions, and you know there seems to be an improvement, but I'm sure more can be done. Thank you.
Thank you. Thank you, Kamen.
This is quiet sun. Did I mention this is completely quiet sun?
Do we have questions? Yes, we have a question.
It could be much more than a question if you want. Yeah, solar radio imaging is magic. But have you, when you get the gain or the calibration solutions, have you? Sometimes you'll have a baseline that is not quite as good as the others. Have you tried to find that particular one in the k-means clustering, if that makes sense? So you can that there's a particular baseline isn't as good as you want. Do the k-means clustering and try and find which cluster relates to that.
In the calibration solutions?
Yes. Or yeah.
No, I haven't done it. I was talking to Mattia yesterday, and he said that they were doing that on some observations. But that's definitely something can be done. In fact, those things can be combined. Mm-hmm. But I know that already. I mean, I know that the data we get are flagged already. For supposedly bad baselines, but I don't know if you want to say something more.
The thing is that depends how bad is a bad baseline, right? If there is like a observation like this, then usually it's because of RFI, so you will see it. But if you have like a solar flare or like a ionospheric effect, then it's a bit more tricky because you have a time evolution of the bed antenna, and that is not flagged because the only flagged part is based on the RFI or if the calibration solution doesn't converge.
Yeah, I mean, definitely something to explore in the future, or even combine with this type of stuff. Yeah.
Okay.
Just to finish up on that, I think about the point, what to consider is like rather than maybe trying to automatically find the appropriate clusters, start with something that you know should have an effect and remove that, and then
supervise it.
Yeah, kind of. Yeah, I'm sure I'll chat to you afterwards.